following 8 properties can be used whenever you're doing operations with vectors. The commutative property just basically says it doesn't matter which order you add them in, they're the same. You can group them using the associative property. Anytime you add u to the 0 vector, you get u back. And anytime you add u and negative u, you get the 0 vector. You can group and distribute scalars as well. And 1 times u is equal to u, 0 times u is equal to the 0 vector. And that's a very important distinction. Notice the difference between 0 and the 0 vector. We're not talking about a number 0 here. You can multiply scalars and vectors, but you cannot add scalars and vectors. So something like 5 plus the vector 1, 2, that does not exist. Some people try to look at it and just add 5 to each component, but that actually doesn't exist, so it's not defined. The length of a scalar multiple, we talked about this a little while ago, but you should know that the magnitude of CV is equal to the absolute value of C times the magnitude of V. It does change the direction of a vector as well if C is negative, but we're only talking about the magnitude here. And this one is pretty easy to verify using the distance formula. A special thing that we sometimes look for is a unit vector in the direction of another vector. This steals the direction while having a magnitude that's really easy to work with, and there's some applications that we'll look at as we go forward that need that. If v is a non-zero vector in the plane, then the vector u, which is v divided by the magnitude of v, or you can think of it as 1 over the magnitude of v, which is a scalar, times v, has length of 1 in the same direction as v. So if my v is 4, 3, the magnitude of v is the square root of 4 squared plus 3 squared, which is the square root of 16 plus 9, or the square root of 25, which gives me 5. So u would be 1 over 5 times 4, 3, or the vector 4 fifths, 3 fifths. We're also very interested in what we call the standard unit vectors. These are 1, 0, and 0, 1. We call them special letters I for 1, 0 and J for 0, 1. And V, which would be V1 times I plus V2 times J, is called a linear combination of I and J. And the scalars V1 and V2 are called the horizontal and vertical components of V. So if we have a vector, for example, V equals V1, V2, what we do is we write that in terms of I and J. So if you break this down into its components, you could write it as V1, 0 plus 0 V2, or V1 times 1, 0 plus V2 times 0, 1, or V1 I plus V2 J. So if we were to locate the point V1, V2, you could think of it as the resulting vector of V1 copies of I plus V2 copies of J, and then this would be V1 I plus V2 J, or the vector V. So a vector like V, which is negative 5, 15, would be negative 5I plus 15J. Another way to represent vectors, and this one is very important and will come back up in a lot of applications. If u is a unit vector and theta is the angle between the positive x-axis and u, so this is my u, and this is my theta, okay? And there's some ordered pair x, y. We know that if you look at a unit vector, you can find x from the cosine of theta and y from sine of theta. And that's the exact idea here. We're just going to take the x and put it with the I, and the y and put it with the j. So u can also be written as cosine of theta, sine of theta, and cosine of theta I plus sine of theta j. So that's a unit vector, but for any vector v, v would be the magnitude of v times the cosine of theta times I plus the sine of theta times j. So sometimes this is a more convenient way to represent our vectors depending on what we're trying to do with them. So if it says to find a vector v with the magnitude of v equals 6 in the same direction as u equals 0, 3, there's a couple of different ways you could do it. Obviously, you can find the unit vector in the direction of u and then multiply that by 6. Or we could use the formula that we just showed. If you look at the point 0, 3, which would be our q here, if this is our vector u, this angle here is pi over 2. So v then would be 6 times the cosine of pi over 2 I plus the sine of pi over 2 j, which would be 6 times 0I plus 1j. 0I is going to be the 0 vector. And of course the 0 vector plus j is just j, so we get 6j. And if one of the components happens to be 0, we usually just don't write its letter. Now this one says to find a vector v with a magnitude of v equals 5 and in the same direction as u equals -1, 2. There's two different main approaches to take here. If you like the cosine of theta and sine of theta angle, you can absolutely look at the vector here using its points. So this would be -1 in the x direction and 2 in the y direction. So our vector would look like this. We're looking for the sine of this theta and the cosine of this theta, but remember reference angles tell us we can look at this angle as well. And if with pluses and negatives being the same, that will work. So this is -1, this is 2. The hypotenuse, c squared, I would get 4 plus 1 equals c squared, so c is the square root of 5. So without knowing what the angle is, cosine of theta is the adjacent over the hypotenuse, so that's -1 over the square root of 5. Sine of theta is the opposite over the hypotenuse, so that's 2 over the square root of 5. And that takes care of the sines and cosines because it's in the second quadrant, which would have a negative cosine and a positive sine. So you could say v equals 5 times cosine of theta I plus sine of theta j, which is 5 times -1 over the square root of 5i plus 2 over the square root of 5j. And then if you distribute that, you get the following numbers. And then if you rationalize to get rid of the radicals in the denominator, multiplying by √5 over √5 in both of these cases, you would get -5 √5 over 5i plus 10 √5 over 5j, and of course canceling out, you get -√5i plus 2 √5j. Now if the trig freaks you out and you don't like that, the other way you can look at it is you can find the unit vector in the direction of u. U is -1, 2. So the unit vector, the magnitude of u, is going to be the square root of -1 squared plus 2 squared, which is the square root of 5. The unit vector would be 1 over the square root of 5 times the vector -1, 2, which is -1 over √5, 2 over √5. And then, of course, rationalizing, you would get -√5 over 5 and 2 √5 over 5. So then v would be 5 times the unit vector. I just want to steal the unit vector's direction. Which will be 5 times -√5 over 5 and 2 √5 over 5. Which gives me -√5 and 2 √5. Now, depending on which version of the answer it wants, these mean exactly the same thing, so you could go from here to this answer. This is just two different ways to look at it. So if the trig kind of bothers you a little bit, you can absolutely use this version where we find the unit vector in the direction first and then multiply by the actual magnitude that we want.